so one of the success for magnetism is in the field of magnetic storage. So if you look at the development of your hard disk drive, the technology that is being used there, so it is almost like represents a 200 years of research which happened in magnetism. Okay, and this technology still will be useful probably for next 10-20 years, but then the magnetism is also going even further into something called spintronics. Okay, so in spintronics, where it is basically electronics but based on your electron spin, not on electron charge. So your normal IC or your chips that works on how you can control the flow of electrons or flow of charge. Okay, so that is basically your current. But now what people are trying to do is, so not now, so maybe for last, let's say 10 years, so what people are trying in research as well as in industries, that you can actually control the spin, and then you can use that as a medium of transformation or transport of information, storage of information, and so on. So magnetism is like, as I said, many times I already told that it is, you can see magnetism in quantum scale as well as in large objects like galaxies and so on. But what we are actually, or the hard disk drive actually comes into the, in terms of the size, it is only, let's say, between some 10 to 100 nanometer. Whatever the technology, the principle that is being used, so that is typically in the dimension of few nanometer up to few hundred nanometer. Okay, so I discussed in the last class a little bit, so I'll skip this. You can have a look when I share the slides with you. So this is basically a historical development of magnetic materials, how they were used as storage devices. So it is actually quite old, the technology to use magnetism for storing information. Although you could not store a lot of information like what you can do now, but nevertheless, you can use magnetic materials, wires, for transferring and storing information. So this is a really good, like if you are interested in history, you can read all those things. So what is the basic thing about magnetic storage? That you want to store information in magnetic domains, basically, right? So domains, you have some specific orientation of your magnetic moments, and you want to, so the one domain, let's say, can store some information. Okay, so that is how, in a modern term, we call it a bit. So a bit of information you can store in a one particular magnetic domain. So not only that, it is not only you store something, but the most important thing is how you can read and write. Okay, so that is the challenge. You can so you can have a book to store your information, but you should know how to read it and how to write also. Or if you want to use a paper or a notebook, right? Unless you know how to read and write, you cannot. There is no use of that information. So then, so we start with the basic, how one can write something on a magnetic material. So this is a very simple, basic principle based on your electromagnet. So this is a animation. Okay. So what you see is here, basically it's just like an electromagnet. So you have wires, where you pass current, and as soon as you do that, so you have some magnetic field lines, and these field lines will basically interact with, if you put any magnetic material close to that, and these field lines are going to affect the magnetic domain, and that's how you can write something. So you can change the orientation of domain using this magnetic field, and that is how you can write it. So how can you read it? So this is again another animation of that. So basically this is like a magnetic material or a tape, for example, or any wire. So where you have these domains, and then when they move along, let's say to the left, so they will produce some magnetic signal, okay, and that signal will be picked up by the same mechanism, because this is like a changing. So this, due to the movement of the domains, so this produces a alternating magnetic field or changes the magnetic field. So that will create or induce EMF in the wire here, and you have to just record the signal. So normally you cannot, so the signal is very low, so you have to also amplify later on, but you can record or collect that corresponding signal with the same frequency and so you have to improve or increase the amplitude, but you can record the signal and look at the frequency, and then that will you can then read it afterwards using other electronics. Okay, so this is a simple mechanism how you can read and write as well, as using the same device. Same principle is based on the same principle. So basically, let's say when you are writing it, you have to put some extra what you need. Let's say if you want to, so this is the same schematic again presented here. So basically you have, so this is called your recording head, let's say, okay. So you might not have seen this magnetic tapes, but if you go to Google and search for magnetic tapes, you will see this cassettes, magnetic cassettes, and so on. So basically you have this recording head, and it is still in a hard disk, it is also called a recording head as well. So the terminology has not changed. So you have the recording head, underneath you have the magnetic material or your storage device. So this can be a wire or can be a hard disk. And then in the first case, so you apply bias, and then you produce a magnetic field, so which is try to align the magnetic moment. So now you can reverse the field direction. So you can write domains like this, pointing along this direction or along this direction. So depending on the flow of the current, okay. So you can change the direction of current, and you can write domains in different directions. So similarly, you can use the same technique to also read it, like I explained before, or you saw it in the animation. So this is just a closer look at how this works, okay. So again, a schematic of that. So you have this record head. So basically, it's as I said, it's a simple electromagnet. So you have the magnetic field, and then you can manipulate the domains depending on how the field lines are. So you can make it strong, you can make it weaker, you can change the direction. So that is how you can change the orientation of your domains. Okay, so what actually you need? So if you want to look at materials, so of course the development is not only based on materials. So there is a lot of electronics is involved, like how you can collect the signal, amplify the signal, how you can move the things mechanically, which is stable. So a lot of engineering is involved there. But here I want to emphasize like what is the role of materials in the in this magnetic storage devices. So the material should always have, it should be something which is, let's say, high enough coercivity. So the coercivity should be high enough that it should not get demagnetized so easily. So that means, so if you have stored some information in some particular domain, so a domain is arranged in a particular way, and that is like one particular bit. So that domain should not be affected by any external field or by temperature. So it should not get demagnetized so easily. So what will prevent that? So that is prevented if the coercivity is high. So that means if the coercivity is higher, so it is good. But again, you do not want it should be too high, because if it is too high, then it will be difficult to write something. So when you want to write something, so that means you want to change the orientation of the magnetization. So you want to move the domains. Now, if you want to move the domains, so you have to overcome its coercive field. So you have to go above the coercivity. So if the coercivity is too high, so you have to apply a lot of current, which is also not desirable. So in that process, you consume a lot of power, produce a lot of heat, and so on. So you don't want also a very high coercivity. So it is again a very delicate compromise between the coercivity value. So also you need a high magnetization. So now, why you need that? Because you want to read it. So these high coercivity, optimum coercivity that you require is due to the constraint on writing. So now, when you want to look at the reading, in reading you need a very good magnetization, so that when the domains move, so this magnetization gives good enough signal that your pickup coil or this coil which are placed above should be able to read it. So the signal is high enough, right? If the signal is low, so then there will be a lot of noises, so you cannot actually detect the actual signal. So therefore the magnetization should be also high. So this is a very delicate compromise between different magnetic parameters of a material, and a lot of research was done. And when these magnetic tapes were used quite a lot in so until even I would say 95 or 2000. So till now magnetic tapes are used. I'm not saying they are gone, but mostly they are used like to store information for like big data. If you want to store your medical information or some weather information, and for a long time. So if you want to save it for like 50 years, 100 years, so it is still people use this magnetic tapes. So one of the reasons is it is very cheap actually. So if you look at the material and the technology, it is very cheap. So you just use simple electromagnet, a magnetic tape where you can just coat or put a layer of these magnetic materials and you can store information. So it is very cheap. So you can store a lot of data using this technology. And when you look at the materials, so one of the first materials was this gamma iron 203. So here I just note down the parameters of coercivity, magnetization, and so this is a ferrimagnet, right? So iron gamma 203 is ferrimagnet, and later on people found this chromium dioxide, so which was much better than gamma iron 203. It is an oxide, but it is ferromagnetic. So remember, I told I think in the class that most of the oxides will be either ferrimagnetic or antiferromagnetic. But there are some exceptions. So chromium, this should be a chromium dioxide, so not Cr2O, CrO2. Okay, sorry, so I'll just change that. So this is chromium dioxide, so which is ferromagnetic, and in 1970s or 80s, it was used quite a lot. But nowadays, for magnetic tapes, people are using some kind of cobalt-based materials. So cobalt and iron, cobalt, and so on. So alloys of that. but historically these two materials were used quite extensively. So now, if you so that is about the storage device. So if you want, what should be the parameters for your recording head? This electromagnet, which is used for reading and writing purpose. So it should have a high permeability and a low coercivity, and of course it should be able to operate at high frequencies. So if you look at these two parameters, so high permeability, low coercivity, and should be able to operate at high frequencies, so immediately you can say, okay, of course this has to be a soft ferromagnet. Okay, so if it is a soft ferromagnetic material, so this fits quite well with those parameters. And so definitely, so the example, as I said, soft magnetic material used like iron nickel, this is called permalloy. And also there is soft ferrites. So this nickel zinc ferrite or manganese zinc ferrite that are actually used as the preferred material for your recording head. Okay. So now we go to another kind of magnetic memory. So this is based on this magnetic tapes and so on, which is not used like in your laptops or your mobiles, but this magnetic memory, this hard disks, that was developed around 1950s. So people started using this magnetic disks. Well, it is basically again a magnetic material, and you can store. So this is, now we are talking about storage in a digital way, right? So the previous, this magnetic tape and so on, were analog devices. Okay, analog storage devices, but these are digital storage devices. That means you store information in 1, 0, 0, 1, and so on. Okay, that is the difference. And now you look at a modern hard disk drive. So you have basically, if you open it, so you have a magnetic disk. It's called a platter. It's a magnetic medium, and then you have this portion. This is your magnetic. Your read and write head or your recording head, and this magnetic read and write elements, the sensors, actually sit very close to the tip here, very tiny, so very small, so few nanometer. Okay, remember, so although this is big, but the actual sensor which is reading and writing is very tiny, and now you can achieve like 10 terabytes of you can store this information. So, and look at how the development of technology that led to, like, you had really huge, these are like huge drums, no? I mean that were used in 1950s, but now this, like, you can hold it in your hand and you can carry it anywhere you want. And of course, if you also compare the price, it is even much smaller, and further it is going down. Okay, so there is two things. So one is you can store more and more information, so you can increase the storage density. Okay, so density means, so you can store more information in a small volume. Okay, so that is the storage density. So basically that you can keep on increasing, and further you can also reduce the prices as well. And this happens due to, again, a big development in research in magnetic materials. So this is a schematic of that read and write head. So like on the bottom, what you see is your magnetic material, which can store. So this strips, what you see is basically again your domains. Right now, what you see is the domains are actually pointing up and down. So this is called a perpendicular recording. So you have the domains which are pointing up and down, and then you have the read and the write head sitting or just above it. So the write head is, again, it's some kind of the same electromagnet based on the same principle. Although the design is different, but it is based on the same design of an electromagnet. So pass a current and you can change the domain orientation by inducing a magnetic field. But the reading part is changed quite a lot. So that technique is called a different technique. It's called known as a GMR, or now it's called a TMR. So GM magnetoresistance. So it is based on magnetoresistance. Okay, the principle. So we'll little bit explore it maybe in the next section. So how much time I have? Yeah, almost there. So I'll just quickly show you two animations. So how this reading and writing. Yes.
It can be visualized as a minuscule
So you see the.
It can be magnetized to a permanent magnet. Every red, blue, or gray block in this picture is a bit. The red blocks have north poles facing up.
Okay, so I'll just play again.
It can be visualized as a minuscule block that can be magnetized into a permanent magnet. Every red, blue, or gray block in this picture is a bit.
Yeah.
The red blocks have north poles facing up.
Okay, so this is how again the writing will work, and how the reading works. Another skill. Okay. So what you see is whenever there is a change in the orientation, so you see a spike. Okay. So that is basically a flux reversal. So this is this point where you see the one, the spike. So this is known as a flux reversal, and that you call as a 1, 0, 1, 0, 1, and so wherever there is a change in the domains, so you see a flux reversal, and that you call as 1, and that is how you can detect your or read your magnetic signal. Okay. So this is how reading and writing works. So we'll discuss in detail how this in modern hard disk drive. So how the role of materials in this reading and writing and storing devices. So we'll discuss about that.